Yes, ma'am.
Okay. Okay, so first question is, for a cell which is given here, the cell potential is found to be 0.43 volt, okay, at 298 Kelvin. And the magnitude of a standard electrode potential for copper, you have to calculate, okay. And what we have given, the electrode potential of Ag plus is given, and the value of 2.303 RT upon F is given, right, which is 0.06. Now calculate the magnitude of a standard electrode potential for copper. So it has been asked in JMIS 2022. Okay, let's see how will we proceed this question. So write down the first half reaction, oxidation half reaction and reduction half reaction. So what will happen at anode? Tell me, reduction or oxidation?
Oxidation.
Oxidation.
So at anode, it will oxidize to copper 2 plus. Okay. And what will happen at cathode? So at cathode, reduction will happen. It will reduce to 2 Ag. Okay. So what will be the overall cell reaction? So from here, this two electrons and two electrons, these will cancel out, and your cell total overall cell reaction will be your copper plus 2 Ag plus Cu2 plus 2 Ag. Okay, this will be your overall cell reaction. Now from here, calculate the E cell. E cell will be, you know that the formula is E naught cell minus 0.06, because the value of 2.303 RT upon F is given, right? So I'm just substituting this value in the formula, 0.06 upon 2 log of C2 plus upon this Ag plus, right? And what's the stoichiometric coefficient over here? 2. So the power will be 2 here. Now substitute the value of E cell. What's the value of E cell which is given in the question? So it is 0.43. 0.43. Substitute this value. E naught cell minus 0.06 upon 2 log. And what's the concentration of copper and Ag is given, right? So the concentration of Cu2 plus is 0.001. Okay, and same for Ag plus 0.01. Okay, now calculate the value, 0.43 E naught cell minus this will give you 0.0. Okay, 0.03. Right, when you calculate this, you will get the log 10. Okay, E naught cell minus, and log 10, what is the value of log 10?
1.
1.
Okay, okay. So you will get this over here. E naught cell will be 0.43 and plus 0.03. So you will get the E naught cell be 0.46 volt. Okay, so your E naught cell is 0.06 volt. Now just E naught cell, this will be equals to E naught Ag cathode minus E naught anode, right? Cu plus 2 plus C. Okay. Now substitute the value. So we have calculated the value for E naught cell, which is 0.46, and the E naught cell of AG is given in the question 0.80, minus we have to calculate the E naught cell of copper ion. Okay, so from here, the E naught electrode potential of Cu2 plus ion will be your 0.80 minus 0.46. You will get 0.34 volt. Okay, or you can write it down like 34 into 10 to the power minus 2 volt. Okay, so what will be the answer over here? The answer is 34. 34 into 10 to the power minus 2. Clear? Please write it down. Once you write, please update me.
Done, ma'am.
Okay, what about you, Mia? Done?
Yes, done.
Okay. Okay, let's move to the next question. Okay, so here's the next question. So the molar conductivity of a conductivity cell filled with 10 moles of 20 ml NaCl solution. Okay, so the 20 ml. So let's write what given over here. And that for 20 moles of another identical cell having 80 ml NaCl solution is this molar conductivity 2. Okay, so the molar conductivity of two solutions are given over here, lambda m1 and lambda m2. The conductivities exhibited by these two cells are same. Okay, so it is mentioned in the question that conductivities exhibited by the two cells are same. So the relationship between lambda m2 and lambda m1 will be. So there are four options over here. So which options are correct? Let's see. So how will we proceed? We know that molar conductivity, the formula of molar conductivity is K1, right? So for a first solution, it will be K1 into 1000, right, upon the molarity. Okay. So for first NaCl solution, first NaCl solution, I'm writing it as 1. Okay. So let's substitute the value over here. So first calculate the molarity M1. So what will be the molarity? It is given mass, the number of moles, right, upon the volume in liter. So what will be the molarity? Just tell me, calculate it. The molarity for the first solution. So it is given here the 10 moles. Okay, so you don't have to find the number of moles. It is given in the question. And what is the volume? So volume is in ml. So you have to convert it into the liter. So it will give you 0.02 liter. Okay, so so you will get 500 moles, 500 molar solution. Okay, now substitute the value over here. For the lambda m1 is equals to K1 into 1000 upon 500, right? So here the relation comes over here. Lambda m1 is equals to 2a1. Okay. Now mark it as equation 1. Similarly, for the second solution, lambda m2 will be same, right? So it will be k2 into 1000 upon m2. Similarly, calculate the value of m2 over here. So m2 will be, what is the number of moles given for the second solution? 20 moles in 80 ml of NaCl solution. So 20 divided by 80 is in ml, right? So 0.08 liter will give. So it is 845. Okay, so it will give you 250 molar solution. Now substitute the value over here. K2 into 1000 upon your 250. Okay, so similarly, lambda m2 is equals to 4 into K2. Okay, mark it as the equation 2. Now see, in the question it is given that the conductivities exhibited by the two cells are same. Okay, so what is given over here? So the conductivities, which is K1 equals to, it is given, right? So from here, you can write this as K2 is equals to the M2 upon 4. Okay. Similarly, for this also, you can write down that K1 equals to lambda M1 upon 2. Okay. Now it is given that K1 equals to K2. So what will you get? K1 will be equals to lambda M1 upon 2, and it is also equals to lambda M2 upon 4. From there you will get this relationship. Okay, K1 will be equals to lambda M1 upon 2, and it is also equals to lambda M2 upon 4. Now applying the given condition on the conductivity. When you apply this condition, conductivity, so you will get this relationship, lambda M1 upon 2, which will equals to lambda M2 upon 4. Okay, because all three are equal, so we can take this equals to this. Okay, so from here you will get that lambda, so 2 1 2, this will cancel out, and from here lambda m2, this will be equals to 2 into lambda m1. Now check which option is correct. So lambda m2 equals to 2 into lambda m1, so it's in option 1, right? So your option A, it is correct. Lambda m2 equals to 2 lambda m1. Got it? Clear, or
Yes.
I need to
Yeah.
repeat the concept? Okay, just write it down.
Done, ma'am.
Let's see the next question.
Done.
Okay. So the third question over here is the specific conductance of 0.0025 molar acetic acid is given, okay, at a certain temperature, and the dissociation constant of acetic acid will be. Consider limiting molar conductivity of acetic acid as 407 centimeter square per mole. Okay, so it's very easy question, right? What is given over here? We know that, see, we know that the relationship, the molar conductivity is equals to conductivity into 1000 upon your concentration, right? Concentration can be molarity, normality, anything, okay? So, and what are given over here in this question? A, conductivity is given, right? The specific conductance, okay. Specific conductance 5 into 10 to the power minus 5, 7 per centimeter. Okay. Concentration is 0.0025. Okay, molar. So we'll just substitute the value in this equation. So the molar conductivity will be 5 into 10 to the power minus 5 into this 10 to the power 3 upon your concentration. Concentration can be written as 25 into 10 to the power 4. Okay, now calculate it. So when you calculate it, you will get 27 centimeter square per mole. Okay, so you get the value of molar conductivity. And your limiting molar conductivity is also given, which is 400 Siemens centimeter square per mole. Okay, so first calculate the degree of dissociation, alpha value. So you know that alpha, degree of dissociation, is equals to the molar conductivity over the limiting molar conductivity. Okay, so now substitute the value over here, 20 upon 400. Your limiting molar conductivity of acetic acid is 400. So you will get 120 over here. Okay. And the degree dissociation constant they have asked. So dissociation constant, the formula is concentration into alpha square upon your 1 minus. And what is concentration here? 0.0025 into your alpha value is 1 upon 20 to 1 upon 20, which is a square, right? Upon 1 minus 1 upon 20. Now calculate this and tell me the answer. The value of dissociation constant. So from here you will get, this will give you 19 upon 20, and this 120 and 120, it will cancel out. When you calculate this, you will get 66 into 10 to the power minus 7. Okay. So what will be the value of dissociation constant? So it will be 66. 66 is your correct answer. The most important thing is to memorize all the formula. Okay. So just go through all the formula and concepts so that you will be able to solve the question. Make a formula chart from all the chapters. Important formula chart. Okay, and revise those formula daily. And Mira and Upsana,
Yes.
Yes.
is it clear?
Yes, ma'am.
Yes, ma'am.
We now see the next question. So here the electrode potential of the following half cell is given. Okay. So the electrode potential of the half cell they have asked, right? And the half cell is this x plus, and the concentration of x2 plus ion is given 0.001 molar, and the y2 plus concentration is 0.01 molar. Okay, and they have asked the electrode potential of this half cell at 298 Kelvin. Okay, and the values of electrode potential of these are given over here. So it's very easy. Solve it. How will you proceed? First, write down the equation, cell reaction over here. Okay, so from here, x plus y plus 2, it is giving you y plus x2 plus. Okay, and we know that what is the formula for E naught cell? E naught cell is E naught cathode minus E naught anode, right? And E naught cathode over here is this, right? E naught of y2 plus y. So just substitute the value over here. E naught cathode will be 0.36 minus, and that for anode is minus 2.36. Minus minus it will be plus, and you will get 2.36 plus 0.36, it will give us 2.72 volt. Okay, so the value of E naught cell is 2.32 volt. Now we know that according to Nernst equation, what is E cell? So the Nernst equation says the E cell is equals to E naught cell minus 2.303 RT upon NF log. Okay, now substitute the value which are given over here. E cell will be E naught cell. We have calculated 2.72 minus, and this is your 0.06. It is given in the question the value of 2.303 RT upon F, and the N value is 2 log, and your what are the concentration given here? For x plus 2, it is given 0.001, and for y ion, it is given as 0.01. Okay, just calculate it, solve it. So 2 minus this will give you 0.03. And see here, when you solve this, you will get the value log 10 to the power minus 1. Okay, and you know log 10 to the power minus 1, it will give you minus 1. So 2.72 and minus minus, it will give you plus 0.03. So your E cell will be equals to 2.75 volt. Okay, or you can write it like this also, 275 into 10 to the power minus 2 volt. Okay, so what will be your answer? So the electrode potential of the following half cell at 298 Kelvin is 275 into 10 to the power minus 2 volt. So this is your answer. So this type of integral type of question they can ask in exam. Is it clear, Upsana and Meera? Is there any doubt in any
Yes.
step?
No.
Okay, Bache, please write it down. Written?
Yes, ma'am.
Yes, ma'am.
Okay. So that's a important question. You can practice more question based on electrochemistry. So for now, we are going to start the D and F block. Okay. Is my screen visible?
Yes.
Yes, ma'am.
Okay. So first, tell me what is D block element? D block element.
Group 3 to group 12 elements are called D block.
Okay. And Apsana, you will tell me what is F block element?
Element whose outermost electrons enters the F shell.
Okay. Okay, so D block elements. So basically, D block elements are the elements in which the outermost electron lies into the D subshell. Okay, so that type of elements are known as D block elements. Like see, from this group 3 to group 12, these are D block elements. Scandium, titanium, vanadium, chromium, these all, right? And these are from 57 to 71 it is lanthanoids, and from 89 to 103 it is actinoid series, which are F block elements. Okay, lanthanoid series and actinoid series, these are F block elements in which the outermost electron lies into the F block, F subshell. Okay, so what are D block elements? So the D block elements in a period contains the elements of group 3 to 12. Okay, in which the d orbitals are progressively filled in each of the 4 long periods, as you can see in the periodic table. Okay, and the elements constituting the F block are those in which the F4F and 5F orbitals are progressively filled. Okay, so do you remember all the elements name of D block and F block? You know how to write the electronic configuration, Upsana and Meera? Because you have already done with class 12, right? We are revising here.
Yes, ma'am.
Yes, ma'am.
Oh, okay, good. So basically, D block elements are also known as transition metals. Okay, so there are mainly 3 series of the transition metals. 3D series just starts from scandium to zinc. Okay, 4D series yttrium to cadmium. Okay, and 5D series lanthanum to Hg, mercury. Okay, and the fourth series is 6D series, which begins with actinium and is still incomplete. So the 2 series of the inner transition metals, which are 4F and 5F, are known as lanthanoids and actinoids respectively. See, so these are the D block elements, and in the bottom, these are F block elements. Okay, so this is from 58 to 71. It is from selenium to ruthenium. It is lanthanoids, and this yellow colored, this shows the actinoid series. Okay, now see, a transition element is defined as the one which has incompletely filled d orbitals in its ground state. When we talk about the ground state configuration, so transition element is defined as the one which has incompletely filled d orbitals. Okay, or in any one of its oxidation state. Let's see. Can I say the zinc, cadmium, and mercury? These are transition metals. So no, zinc, cadmium, and mercury of group 12 have fully D10 configuration in their ground states. That's why they are not regarded as the transition metals. Okay, because the transition metals are those which have incompletely filled d orbitals in the ground state. Okay, but zinc, cadmium, and mercury have fully filled D10 configuration in their ground state, okay, as well as in their common oxidation states, and hence they are not regarded as a transition metals. Remember that. The exceptions you have to remember. Now we have see the positions of D and F block in the periodic table. Okay. Now let's see the general electronic configuration of D block elements. So the general electronic configuration of D block elements are N minus 1, D 1 to 10, from 1 to 10, and S 1 to 2. Okay. In the S orbital, there will be maximum 2 electrons, and in D, there are maximum 10 electrons. So this is the electronic configuration of D block elements. Okay, general electronic configuration. So half and completely filled sets of orbitals are relatively more stable. Okay, so just remember that either half or completely filled sets of orbitals are relatively more stable. Consequence of this factor is reflected in the electronic configuration of chromium, chromium and copper, right? In the 3D series. For example, consider the case of chromium. Okay, so the chromium has 3D5 and 4s1, right? Instead of 3D4 and 4s2, chromium should have 3D4, 4s2 electronic configuration. But instead of this, chromium shows 3D5, 4s1. 3d5 4s1 electronic configuration. Okay, so this is the exception case. Similarly, for copper, what will be the electronic configuration? So for similarly, if I say that 3d 9 and 4s2, right? But instead of this configuration, copper shows 3d 10 4s1, right? Because either half-filled or completely filled sets of orbitals are relatively more stable. So due to stability, copper shows 3d10 and 4s1 electronic configuration instead of this. Clear? So just you have to remember the exceptional case. So the electronic exceptions are copper and chromium. Okay, now let's see the physical properties. So the transition metals, with the exception of zinc, cadmium, and Hg, mercury, right? Because these are not transition metals we have discussed. So the transition metals are very much hard and have low volatility, right? Because they are less volatile. Remember that they are hard and less volatile, and their melting and boiling points are high. Transition metals have high melting and boiling point. Okay. Okay, let's see the melting and boiling point. So high melting and boiling point. Why? Due to the strong metallic bond. Okay, so the transition elements have a strong metallic bond and the presence of half-filled p orbitals, due to which they have high melting point and boiling point as well. Okay. Second point is there is an involvement of greater number of electrons. Okay, there is an involvement of greater number of electrons from n minus 1 into d in addition to the ns electron in the interatomic metallic bonding. That's why it shows the high melting and boiling point. Okay. Another reason of high melting and boiling point is that because of a stronger interatomic bonding, because they have a stronger interatomic bonding between them. Okay, so due to which they have higher enthalpy of atomization, and due to which it results in the high melting and boiling point as well. Okay, remember that. Okay, let's see the trends in melting point of transition elements. So, what happened to the melting and boiling point? First, we will discuss the melting point. So, when we move along the period from left to right, what happens? The melting point of these metals first increases to maximum. Like, see, we have discussed for 3D, 4D, and 5D series. Okay, so different series. Let's see what happens when we move along the period from left to right. The melting point of these metals first increases to the maximum and it decreases regularly towards the end of the period. Okay, see the trend over here. So what happens? The melting point first increases to the maximum and decreases regularly towards the end of the period. Okay, so the melting point of these metals rise to a maximum at D5. At D5 configuration, the melting point of these metals rise to the maximum, except the values and anomalous values of manganese and your Tc. Okay, except these values, so maximum melting point of these metals maximize at D5. Okay, and it fall regularly as the atomic number increases. When the atomic number increases, it fall regularly. Clear? What is Tc? What is the name of Tc? Remember? It is,
Technetium.
yes, it is
Tech.
technetium. Yes, good. Manganese and technetium. So now the trends of melting point of 3D, 4D, and 5D transition metals we have seen, right? So, and now see the strength of interatomic bonds in transition elements is roughly related to the number of half-filled d orbitals. So in the beginning, number of half-filled d orbitals increases till the middle, right? See, number of half-filled d orbitals increases till the middle of the period, which cause the increase in strength of interparticle bonds. But what happened? The pairing of electrons in d orbitals occurs and the number of half-filled orbitals decreases, which also causes a decrease in melting point. I'm repeating what happens when the number of half-filled d orbitals increases till the middle, right? So what happens? The pairing of electrons in d orbitals occurs and the number of half-filled orbitals it decreases, which also cause decrease in the melting point of the transition metals. Okay, so these are all about the melting point. Now let's see the enthalpy of atomization of transition elements. Okay, so in this graph, there is a it is 3D, 4D, and 5D, right? These have they have discussed the series 1, which is a 3D series, series 2, which is a 4D series, and series 3, which is a 5D series. So you can see that it is the highest enthalpy of atomization is seen in 5D series, right? So which is shown in the red color, right? So this is for 5D, right? This is for 4D, and this is for 3D. So from the graph, you can see that the it has the highest enthalpy of atomization and it has the lowest. Okay. So greater the number of valence electrons, stronger the interatomic attraction. We know that the number of valence electrons, if it is greater, then what will happen? The stronger is the interatomic attraction. Okay. So if the stronger is the interatomic attraction, the stronger bonding between atoms resulting in high enthalpy of atomization, as in case of 5. Okay, so in the case of 5D, what happens? The stronger bonding happens between the atoms, which results in a higher enthalpy of atomization, right? And just opposite of that in 3D series, we can see. And the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. Yeah, just remember that. It's important. So metals of the second and third series have greater enthalpy of atomization than the corresponding elements of the first series. Okay, so we have discussed the enthalpy of atomization. Now let's discuss the atomic radii and ionic radii. Okay, so what happens to the atomic radii? So atomic radii of first series decreases till the middle, okay, with an increase in atomic number. So when the atomic number increases, so the atomic radii of first series, it decreases till the middle, but with an increase in atomic number. See here. So the atomic or ionic radii first decreases till the middle, right? Becomes almost constant. In the middle, it becomes almost constant, and then it increases towards the end of the period. Okay. So when the atomic number increases, what happens? First, the atomic radii decreases till the middle, and it becomes almost constant. And after that, at the end of the period, it somehow increases. Okay. This chapter is very theoretical type. You just have to remember all these trends, all these exceptions, and all. Okay. So the new electron, what happens? The new electron enters a d orbital each time the nuclear charge increases by unity. Okay. So, but the shielding effect of a d orbital is not that effect. When a new electron enters, what will happen? the shielding effect will happen, right? But in the case of d electron, it is not that effective. So hence the net electrostatic attraction between the nuclear charge and the outermost electron, it increases. Okay, and the ionic radii, it decreases. Just remember that. Okay, so what will happen when the net electrostatic attraction between the nuclear charge and outermost electron, it increases, so the ionic radii will decrease. It is just inversely proportional to that. However, the increased nuclear charge is partly cancelled by the increased screening effect of electrons in the d orbitals, right? So the increased nuclear charge is partly cancelled out by the increased screening effect of electrons, right? When the increased nuclear charge and increased screening effect balance each other, what will happen? The atomic radii becomes almost constant. When the nuclear charge is increased, right? So when the nuclear charge increase, the screening effect also increase. So these will balance each other, and the atomic radii becomes almost constant. Neither it will increase nor it decrease. Now see, increase in atomic radii towards the end may be attributed to the electron-electron repulsion. So why the in the end of the period the atomic radii increases? So due to the electron-electron repulsion, it increases. Okay. So what happens? See. So due to electron-electron repulsion, the atomic radii, it increases, right? So the radii, it will increases due to electron-electron repulsion. In fact, the pairing of electrons in d orbitals occurs after d5 configuration. And yeah, in d5 orbitals, pairing of electrons occurs after the d5 configuration. Okay? Yeah. And the repulsion attraction, which is electron-electron repulsion, between the paired electrons causes increased in atomic or ionic radii. Okay, so the repulsive interaction between the paired electron, it causes increase in atomic or ionic radii. Now let's see the trends in atomic radii of transition elements. So see, as you can see that the atomic radii of 4D and 5D series are almost equal. Okay, and the radii of 3D is less than that of 4D and 5D. So see here. See, this is for 5D, this is for 4D, and this is for 3D. Okay. Okay, so see here, there is increase from the first 3D to the second series of the elements. You can see that atomic radii, it increases from the 3D to the second 4D series of the elements. But the radii of the third, which is 5D series, are virtually the same as 4D, as you can see in the diagram. Yeah. So the radii of the third series, which is 5D series, are virtually the same as 4D. Why it is so? Because it is due to the intervention of the 4f orbital, which must be filled before the 5D series of the elements begin, right? So it is due to the intervention of 4f orbital, right? 4f orbital, which must be filled before the 5D series of elements, right? So it's due to this, the 4D has a similar radii. 4D series and 5D series have virtually the similar radii, atomic radii. And there is a steady decrease in atomic radii from lanthanum due to the poor shielding of inner core electrons, okay, which is known as lanthanoid contraction. Now see, what is lanthanoid contraction? We will see in the lanthanoid also 4f orbitals, 4f elements. But here, what is because we know that there is a steady decrease in atomic radii from lanthanum, right? From lanthanum, the atomic radii decreases. Why? Due to the poor shielding of inner core electrons. And this phenomena is known as lanthanoid contraction. Okay, the atomic radii contract and it will decrease due to the poor shielding effect of inner core of 4f electrons. And this is known as lanthanoid contraction. Now, here's a question. Why do the transition elements exhibit higher enthalpies of atomization? Okay, so why it is so? Because of large number of unpaired electrons in their atoms, they have a stronger interatomic interaction. Okay, and hence a stronger bonding between atoms, resulting in higher enthalpies of atomization. Okay, so that's the reason behind the higher enthalpy of atomization in transition elements. Okay, let's discuss the ionization enthalpy. So see, due to the increase in nuclear charge, what happens? There is an increase in ionization enthalpy along each series. Each series means along 3D series, 4D series, and 5D series. Okay, so when you move from left to right, okay, so there is an increase in nuclear charge, and due to this, there is also increase in ionization enthalpy. Okay, so ionization enthalpy gave some guidance concerning the relative stabilities of oxidation state also. And we know that the first ionization enthalpy in general increases, right? Although the first ionization enthalpy in general increases, but the magnitude of the increase in the second and third ionization enthalpy for the successive elements is much, much higher. Okay, so see, first ionization enthalpy is less than that of second and then third. The third ionization enthalpy are of for the successive elements are much higher. Okay, so mostly ionization enthalpy, first ionization enthalpy is less than ionization enthalpy second is less than ionization enthalpy of third. Okay, so the third ionization enthalpy is higher among all. See here. So here is some examples of elements given over here. So see, scandium, it is 20, atomic number is 21. There is a configuration over here, electronic configuration. Okay, 3d1, 4s2. For titanium, it is 3d2, 4s2. And here is the first ionization enthalpy, second ionization enthalpy, and third ionization enthalpy. So let's see one by one. Let's see for scandium. So the first ionization enthalpy is 631. Okay. Now the second one is 1200 or 1235, right? And for the third one, it is much higher, 2393, right? So what we can conclude? So ionization enthalpy 1, it is less than that of 2, less than that of E3. Okay. So the ionization enthalpy of third is much higher than the second, than the first. Okay, clear? Meera and Upsana?
Yes, ma'am.
Okay. So the increase in ionization enthalpy is primarily due to increase in nuclear charge. Right. So that's why the nuclear charge increases. That's why the ionization enthalpy also increases. As those transition elements involve the gradual filling of n-1d orbitals, right? So the effect of increase in nuclear charge is partly cancelled by the increase in screening effect. And consequently, due to this, the increase in ionization enthalpy along the periods of d block elements is very small. Okay, now see. So in the 3D series, the ionization enthalpy is much lesser, right? And it is shown that the 5D series has much higher enthalpy, right? Ionization enthalpy in 5D series due to ineffective shielding by 4f electrons. Okay, so the order will be this. 5D will have more higher ionization enthalpy than 4D than 3D. Okay, now let's see the relationship between ionization enthalpy and stability of a metal in a given oxidation state. Okay, so with the help of ionization enthalpy, we can predict which of the two metals in a given oxidation state is thermodynamically more stable. Okay, so let's see, for example, when a metal, for example, a metal has having a zero oxidation state, okay, and it is converted into M2. Okay, so the oxidation state is converted from 0 to +2. Okay, so what happens? The energy here will be energy required is equals to I1 plus I2, right? So first it will convert into +1 oxidation state, then after that it will convert into +2 oxidation state, right? So the energy required here is equals to I1 plus I2. Okay, similarly, if I say if a metal is converted into the oxidation state is initially it is 0 and it is converted into +4 oxidation state. So what is the energy required for this? So energy required for this will be equals to I1 plus I2 plus I3 plus I4. Okay, I hope it is clear. Mera Nupsan, it is clear?
Yes.
Let's see here for nickel. Nickel is being converted from 0 oxidation state to +2 oxidation state, right? So it's ionization enthalpy I1 plus I2. So I1 plus I2 it will be equals to 2.49 into 10 to the power 3 kilojoule per mole. Similarly, for various elements, you can calculate. Okay, so ionization enthalpy, fourth ionization enthalpy, it is much higher. Okay, yeah. If we can compare nickel 2 plus 2 and platinum 2 plus, right? So which one is more stable? So we can see that I1 plus I2 for nickel 2 is less than that of I1 plus I2 for platinum. See here. See, compare these two. So which one is more, right? So this is, so 2.66 into 10 power 3 is more than that of 2.49 into 10 power 3, right? So nickel 2 is less than that of platinum 2. Okay, so nickel plus 2 is less than that of platinum 2. So nickel is more stable, right? So similarly for platinum 4, it is more stable, right? Now compare these two, nickel 4 and platinum 4, right? So in this case, what will happen? So nickel 4, it is a ionization enthalpy of 11.299, which is much more than that of 9.3936, right? So the one which has less ionization enthalpy is more stable. Okay, so if we compare nickel 4 and platinum plus 4, so which one have less ionization enthalpy? So platinum 4 is having less ionization enthalpy, right? So platinum 4 is more stable than nickel 4. I hope it is clear.
Yes.
Okay, now see the oxidation state of different D block elements. So for scandium exists in +3 oxidation state. Titanium, it exists in +2, +3 as well as +4. Okay. For vanadium, it is +2 to +5. Chromium to +2 to +6. It exists. Likewise, so these are the oxidation state of different P block elements, transition elements. So one of the notable features of a transition elements is that it has a great variety of oxidation states, right? It may show in its compounds. And the stability of a particular oxidation state, it depends on the nature of the element with which the transition metals form the compound, right? So stability depends on the oxidation state. Now see, the elements which give the greatest number of oxidation state occur in or near the middle of the series, right? Just remember that. The elements which has the greatest number of oxidation state, like C. So these occur in the middle of the series, like manganese, like iron, right? Like chromium. So these lie in the middle of the series. Manganese, for example, it exhibits all oxidation states from +2 to +7. Okay, so manganese show variety of oxidation states. Elements in the beginning of the series, it exhibits fewer oxidation states, right, which have smaller number of electrons. Why? Why they show fewer oxidation states? Because they have a small number of electrons in which they lose or contribute for sharing. Okay, see, like for scandium, it shows only +3 oxidation state. So the elements which are in the beginning of the series, they exhibit fewer oxidation state. Elements at the end of the series, they shows fewer oxidation state as well because they have too many electrons in d orbitals, right? So they have few vacant d orbitals also, which can be involved in bonding, like in the case of zinc. Okay, so it shows only +2 oxidation state. Yeah. Now the lower oxidation state, if the if the element has lower oxidation state, right, so it will show a covalent character. Just remember that. And if it exists a higher oxidation, it exists in higher oxidation state, so it will form ionic bond. Means its character is ionic character. Okay. And if the higher oxidation states are more stable, and we know that higher oxidation states are more stable than form heavier members. Okay. For example, in group 6, uh, molybdenum, right? Molybdenum and are more stable than chromium. So chromium acts as a strong oxidizing agent. Okay, molybdenum are more stable than chromium. That's why chromium 6 acts as a strong oxidizing agent. And the highest oxidation state is +8, which is shown by ruthenium and osmium. Okay, osmium and ruthenium shows the highest oxidation state, which is +8. Right, molybdenum and tungsten, which are stable than chromium. Now see, the low oxidation states are found when a complex compound has ligands, right? The low oxidation states are found when a complex compound has ligands capable of pi acceptor, okay? Pi acceptor character in addition to the sigma bonding. For example, in nickel NiCO4 and FeCO5. What is the oxidation state of nickel and iron here? It is 0. Okay, so in the low oxidation state, they are found when complex compounds are ligand capable of pi acceptor character. Let's see the trends in stability of higher oxidation state. So the compounds with fluorine and oxygen, they show stability. Stability. Let's see the stability of in the compounds of fluorine and oxygen. Like see, the ability of fluorine to stabilize the highest oxidation state is due to either high lattice energy, like in the case of if we talk about the COF3, okay, so it has a high lattice energy. And when we talk about in case of VF5 and CRF6, so here there is a high bond enthalpy. Okay, so there is a high bond enthalpy. So it is a stable compound. Now, the ability of oxygen to stabilize the highest oxidation state is due to its ability to form multiple bonds with metals. Because oxygen has a ability to form a multiple bond with metals, right? So, it stabilizes the highest oxidation state, right? Due to its ability to form multiple bonds with metals. Now, see, there are some stable halides of first transition metals. Okay. Now, see, like for in +6 oxidation state, CrF6 is a stable halide. Okay. For +5 oxidation state, VF5 is a stable, CrF5 is a stable halide. For +4, CIX4, and X could be from chlorine to iodine. Fluorine, chlorine, bromine, iodine over here, right? And +4 oxidation state, VX41. And 1 here is telling that here from fluorine, chlorine, bromine only, not iodine, right? So likewise, you can see this table to uh, to learn that stable halides of first transition metals are there. See, okay. Now see here for +1, which is the lowest oxidation number. So here copper copper halide also exists, right? Copper halide is a stable halide, and here X3 is chlorine, bromine, and iodine over here, right? Chlorine could be, it can be chlorine, bromine, or iodine. So these are some stable halides of first transition elements. Okay, now see, the highest oxidation numbers are achieved in tetrahalides. Okay, tetrahalides like TiX4, VF5, and CrF6. And the +7 state for manganese is not represented in simple halides such as, now see, in MnO3F, right? These are the stable halides. You know, see, yeah. Now see the standard electrode potential. See, just a second. Yeah. So for the first row transition metals, the standard electrode potential values are these. Like see, for vanadium it is -1.18, chromium it is 0.91, manganese it is 0 -1 point, and so on. Okay. Now see, the electrode potential values are not regular, which can be explained from the irregular variation of ionization enthalpy, right? And also the sublimation enthalpy, which are relatively much less for manganese and vanadium, right? That's why it doesn't follow the regular trends over here, right? So first, you can see that from vanadium to chromium, it is decreasing, right? So it decreases from -1.18 to -0.91. And after that, after chromium, it's slightly, it increases from -0.91 to -1.18. After that, it also decreases, then decreases, then decreases, and again it increases in a positive way. So the values are not regular, which can be explained from the irregular variation of ionization enthalpy, right? And also the sublimation enthalpy, which are relatively much less for manganese and vanadium. See here. So this is a standard here. We have taken on the y-axis standard electrode potential, right? And on the x-axis, these are the series, right? Vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So here you can see that the electrode potential value for copper is positive. Okay, right? So the greater amount of energy required to transform the copper into copper 2 plus. That's why the electrode potential of copper is positive over here. So due to the positive the electrode potential, the copper doesn't liberate hydrogen from acids. Remember that, right? Because the copper electrode potential of copper is positive, due to which it doesn't liberate hydrogen from acids. And the general traits toward less negative electrode potential values across the series is related to the general increase in the sum of the first and second ionization enthalpy. Okay, and it is very interesting to note that the value of E naught value for manganese, nickel, and zinc, they are more electronegative. They are more negative than expected. Okay, they are more negative than expected from the brain. Just write it down. Okay, and the stability of the half-filled D shell in Mn2 plus and completely filled D10 configuration in Zn2 plus are related to their E naught values. Okay, we can relate these values Mn2 plus and Zn2 plus. In Zn2 plus, there is a completely D10 configuration. Okay, and Mn2 plus, it is half filled D, these subshell. So we can relate these E naught values of these two. Similarly, for E naught, whereas the E naught for nickel is related to the highest negative delta H naught hydration. Okay, now see the chemical reactivity of D block elements. So the transition metals vary widely in their chemical reactivity. So many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble gas, right? So that is why they are unaffected by simple acids. And the metals of the first series, with the exception of copper, are relatively more reactive than and are oxidized by 1 molar H plus. Okay, except the copper one. Yeah, just see that. And the E naught values of M2 plus M indicates a decreasing tendency to form divalent cations across the series. Okay, so in general, trend towards less electronegative values is related to the increase in the sum of first and second ionization enthalpy. So we have done this. Now let's see, it's very important. Sometimes they ask the questions based on this magnetic properties. The compound, the electrons elements are paramagnetic or diamagnetic. Just calculate it. This type of question. Okay. So let's see the magnetic properties of D block elements. So the magnetic, due to the unpaired electrons in d orbitals, many compounds of transition elements are paramagnetic in nature, right? And as the number of unpaired electrons increases, the paramagnetic character also increases. Just remember that. Okay. So what I said is, we know that due to unpaired electrons in d orbitals, many compounds of transition metals are paramagnetic. Okay, so as the number of unpaired electron increases, paramagnetic character also increases, right? Now see, and what are paramagnetic and what are diamagnetic? Let's see. So substances which contain a species, which are atoms, ions, or molecules with unpaired electrons in their orbitals are called paramagnetic. Okay, and paramagnetic substances are weakly attracted by the magnetic field. Okay, and strongly attracted, and sometimes the substances that are strongly attracted by a magnetic field are known as ferromagnetic. Okay, and the substances which do not contain any unpaired electrons means they have all the electrons paired. Okay, and are repelled by magnetic field, they are known as diamagnetic. They are known as diamagnetic type of compound. Now, the transition metals usually contains unpaired of electrons, right? So basically, most of the transition metals are paramagnetic. And as the paramagnetic behavior increases with the increase in unpaired number of electrons. And see, the expressed in terms of magnetic moment, right? And it is related to the number of unpaired electrons. Magnetic moments is related to the number of unpaired electrons. So see how we can calculate the number of the magnetic moment. So the formula of magnetic moment is this. Okay. So just calculate just under root of n into n plus 2. Remember that. And Bm is Bohr magneton, right? This is the unit of Bohr magneton. Now see what is n here. So n here is number of unpaired electrons. Okay, number of unpaired electrons. So by using this formula, you can calculate the magnetic moment. It's very important. Please write it down. A formula of magnetic moment. Okay, just I'm giving you a question based on this question. Write the question over here. Just a second. Okay, write down the question. So the correct electronic configuration and spin only magnetic moment of of GD. Okay, GD is gadolinium, which is a F block elements, lanthanoid series. Okay, gadolinium plus 3. Okay, and the atomic number of gadolinium is given as 64. Hmm. So the correct respectively. Okay. Okay, just tell me the correct electronic configuration and the spin only magnetic moment. Okay. So you have to calculate the you have to write down the electronic configuration first, and after that calculate the magnetic moment. Tell me the answer. Just solve it quickly. Yeah, I'm giving the options over here. 5F7 and 7.9. Okay, let's do this. First, write down the electronic configuration of gadolinium, the nearest noble gas configuration. See, what will be the electronic configuration? So the atomic number is 64. So write down the noble gas xenon, right? And 4F7, 5D1, and 6S2. Okay. Now calculate it for GD plus 3. Okay. So from here and here, 3 electrons will be liberated. And you will get Z7, 4F7, 5D will be 0. So therefore, how many number of unpaired electrons are there? So the number of unpaired, how many number of unpaired electrons are there? Meera?
7.
Yeah. Calculate the magnetic moment will be under root of n into n plus 2 for magnetron. Okay. Now substitute the value 7 into 7 plus 2. 9 7 is 63 over here. 3 root 7. So it will give you 7.93 per magnetron. Directly you can write the answer 7.93 under root 63 per magnetron. So which option is correct? So it is option A, right? Xenon 5F7 and 7.9. Written?
Yes.
Okay, so that's how you can calculate the magnetic moment value. Okay, so these are some ions, its configuration, their number of unpaired electrons, and the calculated and observed magnetic moment. Okay, so you can calculate this also. Okay, now here comes the formation of colored ions. So some ions it form a colored ions. So when an electron from a lower energy, right, from lower energy d orbital, it excites to a higher energy, right? When excitation occurs from low energy to a high energy level, what happens? The energy of excitation corresponds to a frequency of light absorbed, right? And this frequency generally lies in the visible region. That's why the color you will observe. The color observed corresponds to the complementary color of the light absorbed, right? So some ions, it will form colored. I'm repeating what happens when electron, it excites from a low energy to the high energy level. The energy of excitation corresponds to the frequency of light absorbs, right? And the frequency generally lies in the visible region, and the color observed corresponds to the complementary color of the which complementary color the light will observe. You will you will see that complementary color over here. Okay. So the frequency of the light absorbed is determined by the nature of ligand, which type of ligand it is, and which frequency or at which frequency the light will be observed, right? And the light is absorbed. Now see here, for example, for Zn2 plus and cadmium 2 plus, all d orbitals are fully filled. Okay. And for Ti4 plus, all d orbitals are vacant. So there is no dd transition occurs here. So therefore, they do not absorb radiation. So they are colorless. Okay. So due to dd transition, what happens? Because they have no electrons. They have see, in the case of zinc 2 plus and cadmium 2 plus, all the d orbitals are fully filled. Okay, there is no unpaired electrons over here. So and in Ti4 plus, all the d orbitals are vacant. So there is no dd transition over here, right? So they do not absorb radiations. So if they don't absorb the radiation, they will not show any color, right? They will not show any contemporary color. So they are colorless. So this is very important. This is the examples of some ions which don't show any color, right? Because they don't show dd transition, because the electrons are not present there in the vacant, because in the d orbitals, in the case of Ti4 plus, all the orbitals are vacant, d orbitals are vacant, and in the case of Zn2 plus and cadmium 2 plus, all d orbitals are fully filled. Okay, so there is no chance of dd transition over here, so they are colorless. It's important. Okay, now see, formation of complex compounds. how they form a complex compounds. Now see, metal ions bind a number of anions or neutral molecules giving a complex. Like for example, iron, it binds with a number of anions like CN6, 3 minus, and it is a complex molecule, right? It forms a complex molecule. Again, similarly, FeCN6, 4 minus, copper, NH3, 4, 2 plus. So these are the examples of some complex compounds that are formed by some metal ions. Okay. And why some metal ions combined with anions or neutral molecules to give a complex? So it is due to the comparatively smaller size of the metal ions. Okay, so the metal ions have a smaller size and they have high ionic charges over there. So the availability of d orbitals for bond formation is there, right? So there are the availability of d orbitals for the bond formation. So that's why they combine with the anions or neutral molecules and they form a complex. Okay, metal complex. Okay, now see, these transition metals also form the interstitial compounds, right? So, uh, when a small atoms like hydrogen, carbon, or nitrogen, when they are trapped inside the crystal lattice of metals, they are usually non-stoichiometric, right? So, when small atoms like hydrogen, carbon, or nitrogen, they are trapped inside the crystal lattice of metals, they form an interstitial type of compounds. And we know that they are also they are usually non-stoichiometric type of compounds. Like for example, TiC, Mn4n, Fa3H, VH, right, TiH 1.7. So they have high melting points, and due to high melting points and higher than those of pure metals, melting point are higher than that of pure metals. Okay. So, and they are very hard. They are very hard. Some borides are formed. Some borides approach diamond in hardness, right? So they are as much as hard as diamond. Some borides beat the hardness of diamond also. We know that diamond is very much hard in nature, right? And so the uh, some borides approach the diamond in hardness. Okay, and so they retain metallic conductivity and they are chemically inert. They are chemically inert. And yeah, transition metals also form alloy. Because of similar radii and other characteristics of transition metals, the alloys so form are very hard, right? And have often high melting point. Like ferrous alloys, chromium, vanadium, tungsten. These are used for the production of a variety of steels and stainless steel. Okay. And alloys of transition metals with non-transition metals such as brass, which is a zinc, zinc, right? Brass is an alloy in which a copper, which is formed by the combination of copper and zinc. And bronze is an alloy which are made by copper and tin. Okay. Okay, now let's see the catalytic activity. Catalytic activity in transition metals. So the transition metals and their compounds are known for their catalytic activity. And this activity is ascribed to their ability to adopt multiple oxidation states, right? Because we have seen that transition metals which are in between have a variety of oxidation states, right? So due to the variety of oxidation state, they have ability to adopt multiple to form multiple complexes. Okay, like for example, here's an example given. Iron 3, it catalyzes, right? And here the reaction between iodide and persulfate ion is there, right? So here the iodide and persulfate, it combines to form I2 and SO4 2 minus. Okay, now let's see this is the disproportionation reaction, right? So when a particular oxidation state, it becomes less stable related to other oxidation state, one lower, one higher, it is said to undergo disproportionation reaction. Okay. So if the oxidation state, it becomes stable, which when we relate it to the other oxidation state, one with the lower oxidation state and one with the higher oxidation state, then in this case it will undergo disproportionation reaction. For example, here's a reaction given: manganese, right? It becomes unstable related to manganese 7. Okay, so see here the oxidation state of manganese is +6, and here it is 7. Okay, so manganese 6, it becomes unstable. So this is little bit unstable as compared to this manganese 7. Okay, so in acidic medium we are talking about. So in acidic medium, manganese 6, it becomes unstable relative to manganese 7. Okay, manganese 7 and manganese 4. Okay, now see the oxides and oxo anions of metals. Okay, so oxides and oxo anions. So the elements of first transition series form variety of oxides of different oxidation states, right? Different oxidation state having the formula of MO, metal and oxygen, M2O3, M3O6, MO2, MO3. These different type of these form the variety of oxides of different oxidation states. Okay, and these are the general formula of that. And these oxides are generally formed by heating the metal with oxygen at high temperature. And basically, these oxides are how it is formed. So it is formed when we heat the metal with oxygen, right? And when a high temperature, when we heat that at a high temperature, then these oxides are generally formed. Okay, now let's see the nature of the oxides which have been formed. Like for example, for scandium, oxides is Sc2O3, right? And this oxide is basic in nature. For Ti, so it is for titanium, it is TiO. Titanium show form TiO, which is basic, Ti2O2, which is also basic, and TiO3, which is amphoteric, right? Because we know that these transition metals show a variety of oxidation states. So it will form different type of compound oxoacids, right? Oxoacids on the basis of its oxidation state. Like for vanadium, it is VO. If it form VO, it is basic in nature. V2O3, it is basic in nature. VO2, it is amphoteric in nature. V2O5, it is acidic in nature. Okay, similarly, you can see for all these. For zinc, it is ZnO, because we know that zinc has only one oxidation state. So it shows it form only one acid, oxygen compound. Okay, which is a amphoteric. ZnO is amphoteric in nature. Now see, here's a trick in general. Lower oxidation state metal, it shows it isn't basic in nature. If the metal has lower oxidation state, it isn't basic. It is basic in nature. And if the oxidation state of metal is high, then the nature will be acidic. Okay. And in the intermediate oxidation state, okay, so it is in amphoteric nature. For example, let's take example of manganese, oxides of manganese. So MnO, right? So here the oxidation state +2, right? So in lower oxidation state, what is the nature? So it is basic. Okay, like see Mn manganese. If the oxidation state of manganese is +3, then see Mn2O3, right? So it is again a lower oxidation state. So it is basic in nature. Now see Mn3O4. So here the oxidation state is +8/3, which is an intermediate oxidation state. the when our acids see, when a transition state, when it forms oxo acids, so it will, when it is in intermediate oxidation state, it will form an amphoteric type of compound. Okay, and now see, it is also intermediate, so it will form amphoteric in nature. And Mn2O7, which is a higher oxidation state of this metal, manganese, so it is in acidic condition, acidic nature, it will sustain. Okay. So that what I said, oxides and oxo acids of metals. Just remember that lower oxidation, if it is lower oxidation state, then it is basic, higher than acidic, then intermediate oxidation state, then it is amphoteric in nature. Okay. Now in your syllabus, there are in transition metals, you have been given two compounds which are potassium dichromate and MnO4, potassium magnate. Okay, so we will see potassium dichromate, its preparation, its structure, its properties, and everything. So here it is, potassium dichromate. So the dichromates are generally prepared from the chromate, okay, which in turn are obtained by the fusion of chromite ore. Okay, now see. So first, this is the preparation. So in your syllabus, there's a preparation given, its structure, properties, right? Color dependence on pH, interconversion. So we will discuss all these over here. E2Cr2O7. So the preparation. So basically your potassium dichromate, it is prepared from chromite ore. What is chromite ore? So chromite ore is FeO. FeO or Cr2O3. Or you can write it down FeCr2O4 also. So this is your chromite ore. Okay. So there are several steps or of formation of this potassium dichromate. First step is your conversion of chromite ore to sodium chromate. Right. So first, this chromite ore is being converted into sodium chromate. Yeah. So see, when you give a free access of air to this chromite ore in the presence of sodium or potassium carbonate, so you will get sodium chromate over here. Okay. So in the first step, what we are doing, we are converting the chromite ore to sodium chromate in the presence of air, excess air, and sodium or potassium carbonate. Okay, so this is the first step. So what is the second step? So the yellow solution of sodium chromate is filtered. Yeah, see. So you will get over here, this is the yellow solution. You will get yellow solution over here. Okay, so the second step will be you you have to filter the yellow colored solution of sodium chromate and then acidify it with the sulfuric acid. Now put some sulfuric acid to it to give a solution from which orange sodium chromate. Okay. Now see what will happen when you add acid to the sodium chromate solution. So it will form Na2Cr2O7. Okay. So what we are doing? So we are converting the sodium chromate to sodium dichromate. Okay. So this is basically a conversion of sodium chromate to sodium dichromate. Okay. And what was in the first step? We have done conversion of chromite ore to sodium chromate. Okay, and sodium chromate is yellow colored solution. Now, the third step will be the conversion of sodium dichromate into the potassium dichromate. Okay, so we have converted the sodium dichromate into the potassium dichromate by adding a potassium chloride to it. Okay, in the sodium dichromate, just add a pinch of potassium chloride and you will get a potassium dichromate K2Cr2O7 over here and a salt NaCl. Okay, so these are the preparation is of 3 steps. First, what we have done, we have converted the chromite ore to sodium chromate. Okay, then we have converted that sodium chromate to sodium dichromate by adding sulfuric acid to it. The third step will be your conversion of sodium dichromate to potassium dichromate. Okay, and we are adding the potassium chloride over here. Okay, now see the oxidation state of chromium. See here, chromium, chromate, and dichromate is the same. See, the oxidation is same. Oxidation is same. Oxidation state. So, and we know that the chromium ion is tetrahedral. Chromate ion it is tetrahedral, whereas the dichromate ion consists of 2 tetrahedral sharing one corner with CR bond angle of 126. Let's see how. Let's see the structure of chromate ion. So this is the structure of chromate ion. Okay. So the structure of chromate ion is tetrahedral, right? And that for dichromate one consists of 2 tetrahedral sharing, right? One corner with CR bond and which is a bond angle of 126 degree. Okay. So these are the structure of chromate ion and dichromate ion. Now see, sodium and potassium dichromates are strongly oxidizing agents. Okay, and the potassium dichromate is used as a primary standard in volumetric analysis. We use the potassium dichromate in primary standard as a volumetric analysis, which is in titration. In titration, we use the potassium dichromate as a primary standard solution. Okay, so in acidic medium, its oxidizing action can be represented as like this. Okay, so in acidic medium, we can represent the oxidizing action of potassium dichromate as like this. Okay. Okay, now let's see. Just a second. Yeah, we will see the properties one by one. The properties of potassium dichromate, E2Cr2O7. First is your color dependence on pH. Color dependence on pH. Okay, so see in alkaline solution, what is the pH? In alkaline solution, we know that the pH is greater than 7, right? And the color of, what is the color of Cr2O7, 2 minus dichromate ion? We know that the color of dichromate ion is orange, right? Right. So what happens in alkaline solution, which is in pH greater than 7, this orange color, the dichromate ion, it changes to yellow color, right? This changes to yellow color. Why? Due to the formation of CrO4 2 minus. Okay, chromate ion. This dichromate, which is in orange color, right? This dichromate ion solution, which is a orange color solution, it changes from orange to yellow color solution. Why? Due to the formation of CrO4 2 minus ion. CrO4 2 minus ion is chromate ion. Okay, so it is basically the first property is it is a color dependence on pH. Color depends on the pH. When the pH increases like from 7, like 8, 9, 10, like in alkaline medium, right? In alkaline medium, we know that the pH is greater than 7. Okay, so when you take a alkaline solution, so this orange color of dichromate it changes to yellow color. Why? Due to the formation of chromate ion. Chromate ion is yellow color solution. Okay, so let's see the reaction. And the reaction which are involved in this K2Cr2O7, right? It is a reddish orange color. Orange color, reddish orange. Okay, when you add, for example, in alkaline medium, you are adding a base in it, alkali, KOH, potassium hydroxide. So what will happen? It will form K2CrO4, which is a yellow color, and water will liberate out. Okay, so due to this, it changes when you increase the pH or when in alkaline medium, the color changes from orange to yellow, which shows that it is a the color dependence on pH. Now see, second one is your interconversion of K2CrO4 and K2Cr2O7. Okay, so what happens on acidifying the K2CrO4 solution, the color changes to orange red due to the reformation of dichromate, just opposite of first one. Okay, so what happened when you take K2CrO4, potassium chromate it is, not dichromate. So when you add in acidic condition like H2SO4, so what will happen? This is yellow color solution, potassium chromate, right? So in acidic medium, it changes from yellow to orangish. K2Cr2O7 means this potassium chromate it just converted into potassium dichromate. Okay, so here it is interconverted into a dichromate plus K2SO4 plus water. Clear? So just opposite of first one, interconversion of K2Cr2O4 and K2Cr2O7. In this case, when you add an acid with a potassium chromate solution, then this yellow color solution it turns into a orange color solution, which confirms that here the potassium chromate interconvert into the potassium dichromate. Okay. So what is the reason of interconversion? So we know that in dichromate solution, the orange, red, this is orange. See, what is the reason behind this interconversion? So in the dichromate, right, in the dichromate solution, the orange, red, just Cr2O72 minus. This is the ion, right? And this is invariably, it is in equilibrium with yellow CrO4 minus, right? So this ion Cr2O72 minus, this is an orange color, right? This is in equilibrium with this chromate ion, yellow, which is yellow color solution. That's why it is in equilibrium. So it interconverted into that dichromate one. Okay. Now see, third is oxidizing properties. Oxidizing properties. In acidic conditions, acidic medium. Yeah. So potassium dichromate, it acts as a good oxidizing agent, right? See K2Cr2O7, it acts as a good oxidizing agent in acidic medium, right? And it oxidizes basically iodides, sulfides, iron, nitrites, etc. Okay, just remember that it is a good oxidizing agent. And now the uses of potassium. Let's see what are the uses of potassium dichromate. So first use, as I say, see, first use it used as an oxidizing agent in organic chemistry, right? It's used an oxidizing agent in organic chemistry. Okay. Second use in volumetric analysis means in titration for tanning of leather we will use, right? See, another use we will use in the volumetric titration, volumetric analysis, right? Another use is this. We use this potassium dichromate in the for tanning of leather, right? And in we also use this in chromine chloride test. Okay, so these are some uses of potassium dichromate. Now let's see for the potassium permanganate. Okay, at least we today I'm trying to cover the P block elements. Okay, and tomorrow we will start the F block elements. In F block elements there are just lanthanoids and actinoid series. Okay, and lanthanoid contraction and its consequences, some general characteristics of that. Okay, so we will discuss it tomorrow. Today we will cover the D block elements only. So let's see the potassium dichromate. Second compound is here potassium permanganate. What is the formula of potassium permanganate? KMnO4. Okay. Now let's see first the preparation. Okay. So potassium permanganate, it forms from pyrolusite or MnO4. Just okay. So from it preparation, it can pyrolusite ore. What is pyrolusite ore? MnO2. Okay. Now let's see the preparation. So MnO2, when you in basic medium, in alkaline medium, 4KOH, and in the presence of oxygen, when you give heat and oxidizing agent. Okay, potassium nitrate oxidizing, it acts as an oxidizing agent, and here oxidation will occur, and you will get K2MnO4 plus 2H2O. KMnO4 over here. 2KMnO4 plus water over here. Okay, so this is the potassium carbonate. And also, commercially, the KMnO4 is prepared by alkaline oxidative fusion of MnO4, followed by electrolytic oxidation of manganate 6, like C, like MnO2. When you fuse it with potassium hydroxide, right, and oxidized with air or KNO3, so you will get over here MnO4 2 minus manganate. This is manganate ion. Okay, and further, when you do electrolytic oxidation in alkaline solution. In alkaline solution. So you will get the permanganate MnO4 ion over here. Okay, so commercially it is prepared by using this reaction. Clear? Now see the structure of magnate and permanganate ion. What will be the structure of magnate and permanganate ion? Okay. Now see the structure of, first I will see the magnate ion. MnO So what is this? This is a structure of magnate MnO4 2 minus, right? Magnate ion. And both exist in the magnate ions and permanganate ions both exist in a tetrahedral form. And this is permanganate MnO4 minus. Okay, this is magnate and this is permanganate. Both are tetrahedral, right? Both are tetrahedral in structure. And so see here, this is a paramagnet. This shows a paramagnetic character, but this show a diamagnetic character. Remember that. MnO4 minus permanganate, it shows the diamagnetic character, and for magnet it is a paramagnetic character, right? But the structure is same for both, which is tetrahedral. Now let's see the properties of redox reactive properties of, say, MnO4, which is let's discuss the properties of potassium magnate permanganate. Okay, so basically potassium permanganate, it shows oxidizing nature in acidic medium, basic medium, and neutral conditions, right? So it shows an oxidizing agent in all the medium, acidic conditions, whether the condition is acidic, basic, or neutral. It acts as oxidizing agent. Okay, but in the case of potassium K2Cr2O7, potassium dichromate, it shows oxidizing, it is an oxidizing agent in acidic conditions. Okay, now see first in acidic medium. So in acidic medium, so it oxidizes ferrous salt to ferric acid. Okay, so like say KMnO4 plus, so it oxidizes ferrous sulfate to ferric sulfate. Right? So it is converting this ferrous sulfate to, this is ferric sulfate. Okay, now see, it is a condition of acidic medium. Okay, now see in basic medium, in acidic medium, what it is converted the ferrous salts to ferric salt. Okay, and this, and another example is It also converted iodide to iodine. In the same condition. A, this is B part. Okay. In the acidic condition it is. Let's see the reaction. So converting the iodide ions, this iodide ion, it is converted into I2, iodine, right? And water will liberate out. Another example is oxalate to carbon dioxide. It will convert, it will oxidize oxalate to carbon dioxide. Okay, let's see. 2MnO4 minus plus C2O4, 2 minus oxalator plus 16H. Now it will convert this oxalator to carbon dioxide. Okay, 10CO2 plus 8H2. So these are the properties of KMnO4, potassium permanganate. Now, yeah, let's see what if the condition is basic or neutral. If the condition is basic medium or neutral medium. So let's see. So it will convert this to in KMnO4 in basic medium, like when you use potassium iodide and water. So it will convert it into MnO2 and potassium hydroxide plus KiO3. Okay. And in the neutral medium, it will convert in the presence of ZnO, zinc oxide, will convert this into MnO2 plus 4H. Okay, so these are the properties of potassium magnate. So it shows the oxidizing nature in acidic conditions, basic condition, as well as neutral condition. So these are the two compounds of transition metals which are very, very important for your exam. Reactions, structure, its magnetic, paramagnetic character, right? Its preparation, everything is important. So today we have completed the D block